And hello, everybody from MGT 5110. This is going to be a continuation of our last Monday, which we ran into some troubles. I'm going to start over again because we got trapped into some just simple Mac running problems with Excel, trying to find things and make them work in Mac as well as they did in the PC. So I'm going to start over. I'm entering here where we had left off, so there's a visual reference to it. We had gotten here again just for a visual reference. We had gotten here by some notes that we were taking. We had gone through the House of Quality. Okay, so the House of Quality here, and we segued over into the basic statistics we need to answer just a whole slew of challenges in business. Okay, so this becomes valuable in many ways. So just gave you a little visual reference to remember where we're starting from, and I'm going to repeat what I did here to get the momentum going again. And so this first part, I'm going to grab a new sheet here, and I will then repeat everything that I did in here. So hopefully it'll be a little more linear and everybody can understand. The interest with this has to do with a question that I got, and it was very valid, is the question out of chapter 10:1. I had a question from a student, right out of the blocks. You needed to have had the complete explanation of what we were doing here to answer that. So I'll give a fast answer and a long answer version of the chapter 10. So here's the long version of it first. Okay, and so we're going to generate the normal distribution representation. We're going to use a random number generator and get the mean high temp for all these days. And sometimes when I'm looking at this, it deserves to be centered. Make that a little bit easier on the eyes here. Okay, there we go. So we need 20 points here for the last 20 years. What was the temperature on today, Thursday, the 30th of April? What was the high temp? Okay, so I'll get rid of the mean there. It really isn't the mean yet. That's what we're shooting for. Okay, so the high temp for each of the last years. Okay, so this would be 2020, and then we'd have 2019. Okay. They alone could be the record ID. You could use the year for there. Okay. Do that one more time. Something did happen, right? Okay. 20 points. All right. So every year from 2001 to 2020, we're going to go to the data analysis add in here, and we're going to run a random number generator, and we're going to run it on, okay, so we want one variable here, number of points we want are 20. Okay, the distribution, we're going to use normal. Okay, so many things in business, social science, the sort of the wet sciences, I call them, like biology, will behave, their randomness behaves along the lines of normal. Okay, we won't use any of these other ones here, but you have uniform, Bernoulli, you have the rest of these, Poisson. Okay, normal. Okay, we'll make the mean for today. I'm going to guess that it was about 54 degrees. Okay, now what is the meaning of standard deviation? We're going to get into this. Okay, so this lesson is to replicate what we lost on Monday because we kind of got bogged down in some detail with technology, the difference between Mac and PC kind of thing. So we have a mean high temperature of 54 over the 20 years. We're just specifying it. That's the way it's going to run this. It's going to generate the numbers from it. Standard deviation is going to be something like on the order of 5 or 6. And there's a couple ways to understand that, okay? So the standard deviation is like the average distance to the mean of all the points. Of all 20 points to 54, we just take the average. It's like taking the average distance of all of our points, and that's basically what standard deviation represents. It's not exactly that. It's pretty close, and that's the basic meaning of it. But on average, how far away does our data vary from the mean? Okay, so this is also to say, this is going to be jumping ahead, but your knowledge of standard deviation, it helps. Oh, it won't let me do that until I'm done with this. I can't draw anything here, but it says that if you take 54 minus 6 degrees, your standard deviation is 6 degrees, that's 48, all the way up to 54 plus 6 is 60. Okay, so between 48 and 60, we're telling the random number generator that 68% of all the numbers will fall between plus and minus 1 standard deviation. Okay. So we don't worry about the random seed. And our output range wants to know where to put the data. So I'm clicking C5, all right? And I hit enter, and it drops the numbers down in here. Okay, so the first thing is we're dealing with kind of rough numbers here. We're not doing astronomical type of studies or anything like that, or weather studies. We're just using it for like a business reason. We'll go to, all right, 1 decimal. That's probably even saying more than we need to here. So you go to the home menu item, and we're going to knock down the numbers of decimal places to 1. We probably do just fine if we just looked at whole numbers here and ignored the 10th digit in the temperature. Okay, so I'm going to center that up. Okay, makes it look a little bit nicer right now. Okay, all right. So what do we do with this? Okay, this is the way that we take temperature. This is the long path through what we're doing step by step here. Is methodical. Okay, and I'll give a reference in the notes to this video about how to jump to different places and move ahead. Okay, but this is for anybody that really needs the long form of the explanation. Okay, so we recorded data like this, and we might plot it. Okay, so let me grab a pen here. Okay, so we may plot it. If we plot this data, okay, what we would do is probably draw. We would have a plotter out here. Actually, we would be recording temperatures, and it would put what? What would be the middle of here? Probably a reference point of the mean that we start the study out with. Okay, so we're going to start out with a mean of our sample here. Okay, it is something, but what we may end up doing is looking at a local average, right? We might have a weighted average or a running average, right? Where we only are averaging the last, what is that, 7 years, I think, right? Yeah. So maybe we're keeping track and running a 7-year running average on this. We're only looking at the last 7 years. So we would still want to have we're beginning to build population data here. Probably what we would have we'd have our starting population number here, okay? And then from this test that we did, a sample that we did of 20 points, it's going to show this mean is going to be something along here. So this is the mean that is coming from our test data. All right, I'm only going to put a dotted line in there. And what we do is for each of the points, okay, so if you think of this as a scrolling recorder and it's emerging, it's like paper. There's a pen here, like scientific pen. That's like a pen with a little pivot here, and it's putting dots down here for where the temperature is in our data set. Okay, so as we go along, okay, the paper's moving this way. So the earliest point would be 2001, and just emerging is 2020. So, okay, just understand what the time frame here is. Okay, so you have to understand how to use data. This is going to be recorded no matter what you do. This is time series. Okay, so this is time series data, or it's one dimensional, but it's longitudinal. Quite often when people mention longitudinal data, that means over time. Quite often that means over time, okay, as opposed to cross-sectional, okay, cross-sectional. Okay, I'm just bringing terms into here. Cross-sectional data would be, we took all 20 points, here at one time. That's cross-sectional, okay. In this case, we have a running on time. Okay, so time is going along here. And so nothing here is rocket science. I'm just saying the obvious. Okay, so as we go along here, we're going to have 20 readings around. This was the sample mean of the 20 readings that we took, and we're going to have these readings of temperature. Right now, remember, what is the shape? Always draw the normal distribution because it tells us so much. Especially if you're a visual person. Okay, is draw this. Okay, we asked for a mean and we're going to calculate it. Okay, so we asked for a mean. I'll put it down here. I think I said 54, right? I asked for a mean of that. Okay, and okay, we'll leave it at that for now. And so what it says is that most of the time when we take a reading, it's going to occur around the mean. All right, so this is where I was going in class when we kind of sort of got disbanded and disrupted by technology. Okay, the point is make sure you understand what is this drawing here. What is this drawing? Okay, this drawing. Okay, this is a conversion of the data. This is chart 1. If you look at it, this is chart 1 of data. This is just we're charting it again. We're going to chart it a different way. And how are we doing that? Okay, All right, this is the frequency diagram. This is the frequency diagram of the data. Okay, and it says what happens out on the tails happens infrequently. The height of this, you can consider it a count of the times that it happened, or a percentage, or what we should say is a proportion. Okay, the proportion of the time that it got counted. Okay, so these are two different ways to look at it, and they're distinct. They're quite different. Okay, especially when we get into P charts and C charts. That's the difference between a count chart and a proportion chart, just so we have a preview of what's coming up. So when we look at data here, we're trying to figure out what does the normal distribution have to do with the raw data that we have. Well, this, if you notice, it's the same data in here, but we're just counting. It's a counting. We can both count the frequency of recurring numbers here, and the closer it is to the mean, the higher the number of the count is going to be. All right, so the normal distribution can be thought of, the height at any one point can be thought of as the count at that period, at that point, or it could be a proportion. Okay, and so from everywhere from minus infinity to plus infinity, okay, we can look at the area underneath this curve. It's one of the things that we use to exploit any process that operates according to normal distribution. The outcomes are normally distributed. We exploit some properties. We've, basically the world of management has understood that we'll represent it as this curve. We use this every time you do one of these problems. You should really just draw down a curve and make sure you're understanding the numbers that are being supplied to you. Okay, and it says that if we're pretty far away from the mean, we're not going to have very high count. We won't have a very big count here. As we get closer to the mean, it's higher. That is the very definition of the normal distribution. Things near the mean are happening more frequently than far away. So what kind of operation do we do on our data to get to this? Well, we're going to have to sort, right? Because we said that the lower numbers are down here now and the higher numbers are up to the right. So this is just the x-axis here now just shows a range, and in here we do have a range. We have a hard range because there's going to be a low involved here. There's a low number involved in our list of data, and there's going to be a high number in there. It's not the population. It's just a small sample, and it's 20 points. 20 points that we have here. So I'm going through this at length. Don't lose the connection of what this thing is. It's the original data. We just counted up the frequency. All right. So on such a small group like this, what we're going to have to do is there's probably not many repeats in here. Okay. Because when you take a small sample, like we did, of only 20, I'll draw it here and I'll use the same mean. Okay. What we're going to probably get is a lot of ones. We're only going to get a count of one, and a couple of places we're going to get twos. It's a little bit random. So it's not going to have a chance with such a small number of data, or small data set, that it will be able to see this build up here. So there's another way that we can do this is we can group. Okay, we can make groups and we can show a histogram then. Okay, so we can show a histogram, and these are mini ranges within the larger range of data, and so all points that fall between a couple points here. All right, so what we might do is, well, let's start processing this by example. Okay, so how do we get from a list of these numbers to counting the height, how many points there are for any one value in here? Okay, so we could write in a whole bunch of equals counts. That's not a really good way to do it. All right, so what we're going to do is order this data. We have to go through a couple steps because the data sort. Okay, we want to sort on these. We want to order them from low to high, high to low, whatever you want to do. We're going to do from low to high. Okay. We have to work on raw numbers. We can't work on formulas. So the first thing we're going to do is realize that the random number generated has a lot of precision in it. So we're going to have to round this down. So we're going to round these numbers to one decimal place equals round of the number. And we specify, it didn't take, one more time. It's going to equal round of the number, and down to one decimal place. That just shows us a little bit of what's going on here with just one decimal place. So we take that, we've rounded. So over here on the left, we've rounded on the screen. Okay, so we've told it to format, we've told Excel to format the number, just show the first digit rounded. But the underlying number still has the precision. See it up here at the top? It still has all the precision that we start with. Okay, and then we actually round it. So now we're down to losing sort of information here. We've lost many digits, but when we're talking about this temperature, it's not something that we need such great precision over. Okay, now you can't just take a column, unfortunately, and go to data sorting. Okay, if you want to sort this, it throws up a little warning up here. It says, you really just want to work with one column of data? That's all you're interested in? And yes, we do. Okay, so in this case, we're just proving a point. Okay, so if we try to sort on this, we will tell that, let's see if I say this. Yes, okay, so we have my data has a header on it. Okay, and we're going to sort by round. So it gives the name of this column of data, cell value smallest to largest, and if you hit OK, nothing happens. And that's because you cannot sort on something that's computed with a formula like that. We need to have the raw number here. So what we actually have to do is I'm going to grab this data, I'm going to Control C, and I'm going to make another column over here. I'm going to right click on it and just put the values in, okay? So I'm clicking just paste values, okay? You can even see that the format kind of changes around on it a little bit, and so I'm going to have to go back in there. Oh, I can do it this way. I could show one digit of precision, okay? Now we can sort. Okay, so now we'll grab this data again. Now we can go in there and sort. So we go into data, sort, shows that same warning. We said, oh, it's still okay, we don't mind, okay? And it's going to say my data has headers, which it does. Okay, so we're going to sort on sort and smallest to largest. Okay, now it sorts, okay? If you want to just clean up your screen a little bit, we'll just take that and hide the column. All right, because we're not going to really work with that. It's going to be two columns of the same numbers, okay? So now we're going to do a histogram, okay? So we'll use the histogram formula in Excel. To prep for the histogram, what we want to do is we would have to think about this. We kind of have to look at this and figure out what the min and max numbers are to be able to plot them here on a plot over here up in the upper right. To create a plot out of this, we don't need to start at 0. We don't need to end at 1,000, right? What is the range involved here? Let's understand what the minimum, the maximum, the range is here to be able to start setting up a histogram, because we're going to have to create for a histogram a table that shows the divisions, the minor ranges that we want to bundle, everything, for instance, between 45 and 50. All right, we include in a bin. Okay, so when you use the histogram formula here, you're looking to combine these into a bin. It helps us understand and visualize the normal distribution properties of this. Again, it's because look at how many repeats that we have. If you count these up, there's almost no number in here that I see so far that has more than one count. Okay, all right, so this is how we have to help it along to be able to view that we actually have normally distributed data here. Okay, so in order to prep for the histogram formula, we're going to use the data analysis again. Okay, so we want to know some things like min, max, range, and it's going to give us several other things. I'll show you how it's going to show us a few other things here. So I'm going to delete that. And I am going to delete this. Clean it up a little bit. All right. Always keep clean here. All right. So we go to data and we go to data analysis. And what we're going to do is save ourselves a lot of time and use descriptive statistics on this data. This is where we got to in the class. We kind of got interrupted, I think, at about this point. Okay, so we don't want a new worksheet. We want to do an output range. It's going to drop a table of interesting statistics in here. Okay, so we have to tell it where to drop it. Okay, I'm just going to put it right there. Okay, the input range, what are we going to use for the input range? We are going to use, we always have to check these formula whether they want to use a header or not. Okay, so we're going to tell it that it has a label in the first row. Okay, so we've got that, grouped by columns. Output range is set, summary statistics is good, and if you want to look at some further things, you can click off confidence level for mean, kth largest, kth smallest, that's percentiles. We're not going to worry about that for this, okay? So if you click OK, it's going to drop in a nice little table here of all the things we would have had to put in manually, like equals, average, right? We'd have to type all these things in here, and instead we could take a really fast look and do some data analysis on what we have here. So what were we after? We were after the minimum, and we were after the maximum. So our min and max helps us to define the histogram. So now that we use data analysis to get a description set of the data that we have, we need to set up a table for the same thing. We're going to use data analysis with histogram, okay? And so we look at our range here. We have to figure out how many bins we need, okay? So we want more than one bin. One bin would mean everything would be in it. There'd be one, it's like one monolithic block on a column chart here in Excel, right? So we'd have to figure out how many bins, certainly more than one, right? So maybe about 7 is not a bad way to start taking a look. That would give us a center. Also, it's an odd number, so there would be one center that would probably grab the mean. Our mean would probably be reflected within the middle one. So let's go by 7. Let's figure out how big the bins have to be, okay? Now, I don't really have to calculate this, but I'm going to show you what our thinking is. It could be a much more complicated problem than this. All right, so what's the range? The range they gave us was 19.2, so we'll just say equal 19.2 over 7. Okay, so it says about 2.74. Let's use every 3 degrees as a bin. Every temperature that falls within a little miniature range of 3, as we go up the scale here, will count into that bin. Okay, so we're collecting things, we're removing information, if you will. Okay, so we're aggregating the data a little bit, so we lose information. We're just doing a count between this little range and lower limit and upper limit. Okay, so the first number that we have is 45. So we could go from 45. We'll go from 45.0 to 40. Let's format this here. We need about 7. 1, 2, 3, 4, 5, 6, 7. I'll paint it while I have a chance to do that. Okay, so we need to go from, I was going to format this. Okay, so we're just going to format the range. I want to make this textual to begin with. So we'll make the bin ranges 45 to 40, not 8, but 47.9. Okay, and then we'll have 48 to 50.9. And then we'll have 51 through 53.9. And then we'll have 54 through 56.9. 57 through 59.9. 60 through 62.9. So we're making even size. Note these are even sized bins. And then finally 63 through 65.9 doesn't really matter. Okay. All right. So these are going to be the bin sizes, and this is going to be human readable. Okay. Because now we have to put a little table together right next to this that the histogram formula or the histogram function of the data analysis capabilities needs to know. Okay, so what we do is we put the upper end, we just need to put the upper end inclusive of the numbers that will go into the first bin. So we really just need the second number of each of these. So it's going to be 47.9, 50.9. So we have to, if you look what we're doing, we're setting up the edges. So the histogram formula is going to look at this column, okay? 53.9. It'll include everything up to that, okay? 56.9. 59.9. 62.9. Finally, 65.9. Okay, so that is going to be what the actual Excel uses. It's a little bit harder to understand what that column means, and this is what it means. Everything from 45, and it's really going to be 0 or negative infinity up to 47.9. Okay, just so you understand how the histogram works. It's like any number it finds up to 47.9, it will count in that bin. Okay, so let's go ahead and do our data analysis in here. Let's go to data analysis. And we're going to do histogram right there. Okay, let's fill this out. So the input range, click. I'm going to click labels on, okay? Our column has headers. Our columns do have headers in there. And so our sorted data was here, okay? And the bin range wants to know is technically right here. I think it's going to want headers in both of those. I'm going to have to type a header in there. Output options. And we're going to put the output range right next to it, like right here. Okay, we don't just pass on the Pareto, Kuhn percentages, and chart output. Let's go for a chart output, okay? Because that'll save us, that's all that does is save us the task of what we're after. We want to create a chart of that data, and that's going to look like a normal distribution. Okay, so we click OK. There we go. And I'm going to say that this is for the histogram. Histogram. I'll call it function, but it's really a bigger process here. Okay, with the Excel. I'll put it up here at the top for Excel histogram function. Okay, so that's what we input to put it in there. All right. So vaguely we can see that we have a normal distribution. We have so few data points. That's why in class I had gone for 3,600, which was probably too many, but like 360 would be a good number. The reason once you get a column that's 3,600 long, it gets a little bit uncanny to or unwieldy, put it that way, to manipulate the data. But here we have such few data, I think you can understand that we have vaguely can see that there is a histogram behind this, and the more data points we add in, then the more it starts resembling the histogram. Okay. All right. So that's how you get the histogram. You have to just imagine that we had a longer list of numbers, and it came out, adhering more to the classic shape that we have here. So where we've gotten to is, I call this the story of numbers or story of statistics, because this was a long process to go through to show how we get these normal distributions. That's what it looks like. That's the frequency distribution model of it. Okay. Probability mass function, I think they call it. All right. Okay. And it shows the weight. Why they call it like a mass function is it shows the weight is all in the middle. Is most of the weight of the numbers is most of them are occurring around the mean. The mean's in the middle like that. Okay. So that's the purpose of what I went all the way through that with. Is that's how we're going to get to this. If we go too quickly, you're not going to understand, or you're not going to remember, or you're not going to build it into your practice of understanding that there's this normal distribution shape to it. That's where it comes from. Okay, so we went from a stack of numbers here. We had to do a bunch of processes on it, so it ended up looking like such down here. Okay, all right. So that gets us to the point that we understand what this looks like. We have a mean involved. Where's our mean? Okay, so our mean is up here. They list that. That's the most frequently thing. But in order to, and now we're sort of bridging into a new section here. It's like section 2 of the discussion, okay, is how else do we have to define this? Well, we were talking about the range here, okay? So the range for our area, and I made this up. This is for the Hudson Valley area, So the range of our temperature on this date is whatever it is. It's what these randomly generated numbers that we have over here, okay? But pick another place like the North Pole, okay? So what would it look like if we did 20, what's the average temperature on April 30th at the North Pole or South Pole? And it's going to be, I have a feeling it's going to be very much narrower, okay? So its mean, okay, if we plot it with the mean that aligns, see I'm drawing the line all the way down from our top down here. So if I draw the mean there, okay, I'm not really sure, but the mean probably varies a little less, okay? What does that mean? More of the numbers are stacked closely. See, we have more of our data points. If we took 20 data points, it still has 20 data points. The area underneath here is like the volume is 20 data points. This is 20 data points, and this is 20 data points, but many more points are near the mean. Its variability is less. Variability, we'll call it the variance, okay, the variance. The variance is what? It's going to be, the variance is equal to your standard deviation squared, okay? So we normally call it sigma squared is your variance, okay? That's what we call it. All right. So we need a definition about how widely our data is varying around there. Those are the two core things that we need in statistics. So we have the standard deviation. Well, how do we get to the standard deviation? Okay. The concept is this. Okay. It's logical. Okay. So don't get freaked out by the statistics here. The standard deviation has a wacky name to it, but it starts out as a simple concept. Okay. And that's what we're going to build on. We're going to create something called the ADMAP. Okay. The ADMAP, ADMAP. Okay. I'll give you what the acronym stands for in a second. So how would we describe how much the data varies around the mean? We would take the distance from the mean to every point. Okay. So if I choose to use this graph, this chart, to describe what I'm talking about, if I come over some distance from the mean and I find the height of the curve is there, that height means the count or the frequency, that's the count of this value. The height of this, y, is equal to the count of x at that value of x. Okay, so if this mean was 53 point something, that's 53 degrees. If we go some temperature above that, 4 degrees above it, if we go to 57, how many points came in at 57? All right, you have to work this through your mind. In the world of the statistics, you have to push on the data. If you try to just read linearly, maybe you can get it. Maybe you've had statistics before, but you can fool yourself into understanding parts of this, and this is why I go into this in such detail. All right, so the idea there is if we go up 4 degrees from 53, we would have some number of points there. It's at 57 degrees. Out of 100 points, maybe 13 of them were at 57 degrees. To put numbers on this, okay. So this is a count. The height of it is a count. Or if there was 100, you can also look at. We know the n. We know it's 13 over 100 points, like I just said, and so it's 13% is your frequency there. 13% of the time, or the proportion would be 13 out of 100. Would be the proportion out of there, 13 over 100. Okay, the count is 13, the proportion is 13 or 13 out of 100 or 13%. Okay, all right. So you're looking at this curve, you have to know it's not far from the original data. You have to just know that we resorted it and created. In this case, we created a histogram down here, and we created bins for there. And every one of these bins is 3 degrees apart. When you create the histogram, you have to make sure that you use equal bins there. Now, you can cheat a little bit there, too. You could actually, looking at your data, but I don't want to go into that too far, but you could actually, when I say cheat, what you could do is you could actually bend or exploit this in a way that serves a purpose. Okay, you might find that you will find, like, if you do surveys and you collect data, that you have a big skew. Okay, so there's one reason why you might change the size of those bins. You might have a big skew. It's left or negative skewed. And what ends up happening is there's so few points down here that if you stay to uniform bin sizes, that you're going to get a few that have even 0 in them because you're just stretching it out to catch the one that is in there. Okay, so this is another way that we can exploit the data in business, especially like marketing data. Okay, so what we would do is for all where the data is populous through the middle parts here, we stick to a uniform bin size. But when we get down to a tail like this, we might go, oh, well, let's just take all of this as one. Okay. And so there are reasons why you might change the bin size, to be aware of that. But for all that we discuss, the bin sizes are going to be about the same. All right. Okay. So the histogram is especially valuable when we have scarce data like this, because you don't want to have a lot of bins with 0 in there. Okay, you want to collect things together, and it starts assuming this. This almost looks like it has a little left skew in there, but it probably doesn't. It's just that it's an issue of so few points, because we didn't order up any skewness in there. The skewness is here. It's actually listed over here is 0.34, and that's actually telling us that the skew is as I drew it. Okay, if you look at it, it's a positive number. Your skew's to the right. Okay, so this is right or positive skewed. Okay, positive right or positive skewed, and it's showing that, and we can actually visualize kind of. This is sort of a quick test of it, but it has sort of the appearance that it's a little bit right skewed. Okay, so this is probably overkill for the problem. that we're facing here, chapter 10.1, is a straightforward question, but this is what you need as the background to really understand statistics, okay? All right. So we need to get at what is the meaning of this average distance to the mean of all the points, ADMAP, okay? So for every point that we have in our original data, I'll come back over here. Here's our original data, okay? So what I'm going to do is going to move over to another page. So we want to find the average. Remember, the mean is also called the average or expected value. Those are all the same. So here, instead of running around, I'm just going to calculate that very quickly here. We're going to need this. We said we're going to take the average distance to the mean of all the points. So there's the mean, and then for every one of these points, we have to see how far away it is from the mean. We're going to take the average of that. That's the average distance to the mean of all the points, or ADMAP. We have to get the distance from every point to the mean. So there's a point. See how far away it is from the mean, right? Well, we're going to drag this formula down. So we have to use F4 to make sure that we use absolute referencing to that. This is like a reference cell up here that we don't want Excel to auto increment it as we draw it down. So you use the dollar sign, and Excel will understand. Just go to that cell. You can put the dollar signs in front of there. Okay. So I hit enter. So the distance from the point to the mean was 8.1. And now we could see, let's take all the distances. And as you're going to see, some of them come out negative, right? Okay, because some of them are to the left of the mean. Now, again, now's the time. It's a good time to go in there and say, what's going on here? Okay, so we have data that looks like this. Here's our mean, okay? And for all these points, we just saw how far every point was from the mean. That's what we just measured. But what's happening is these are negative numbers and these are positive numbers. Okay, so here's some properties of the normal distribution. First of all, it's highest in the middle. That's the quickest way to say it. Most things happen around the mean. That's property 1. Okay, so there's a central tendency, we call it. That's a central tendency. Things are toward the center, near a mean. Near a mean. What's the other aspect of this? If it's ideal data, it's symmetric around the mean. So for every distance we go to the left, then we get a point. If you go to the right, okay, this would be a negative distance. This would be a positive distance. Okay, so they tend to negate. That's one of the issues that we're going to run into here that just adds just a smallest level of complexity that we have to remember. Okay, so that's what the symmetry means there. Okay. So we'll go along with that. Is symmetric is the other thing. Okay, so we'll work with that right now. So if we wanted to define a number, average distance to the mean of all the points, it's going to come out as a yardstick. It's going to be this long. We're dealing with degrees here. So this is degrees Fahrenheit, don't forget. So the amount that it varies is going to be in degrees Fahrenheit. Okay? This average distance to the mean of all the points. So we got these distances, okay? So I'm going to do a really quick, if this average, if we equal, quick shortcut here, if you want to do the average, is Alt MUA. Select your cell. Let me do it again, didn't take. Alt MUA will give you your average. I just do that so many times. It's a keyboard shortcut that meant something to me. And Excel picked up the right range here. It actually guessed correctly. I hit enter, and here's the problem. The average distance to the mean came out as 0. All right. So how do we fix that? Okay, so let's write that equation down. Right. Our average distance to the mean of all the points is equal to the sum of every point of interest, how far away it is from the mean, that's the distance, divided by n. Okay? And we're going to go from I is equal to 1 to n here in the sum. All right? So the average distance to the mean, right? And that's the problem is because it's symmetric, for every negative number, we're going to get a positive, every negative distance, we're going to get a positive distance. Okay, so what if we just take the absolute value of that? Okay, so instead of just taking the distance, okay, so this is going to be distance absolute. Okay, so we're going to do equals absolute of this cell. We're just going to turn another column here. All these numbers, we're just going to turn into the same number, should be the same number here. And I'm just going to knock down the number of decimal points displayed so you can tell. Okay, so they see every negative number, we just took the absolute. That's wonderful. Okay, so I'm just going to drag my average formula over here. And now I can say that the average distance to the mean of all the points is 4.2. I just locked this thing down. 4.2 degrees Fahrenheit is this yardstick. It's a measurement. And if I overlay it, okay, so here's the big point now. I'm going to draw a little bit larger normal distribution over here. Okay, so we can get at it a little bit clearer. Okay, so here's the mean was whatever it was, 53.4. And we have a yardstick. It's in our hand, and we overlay it on here, and we go, our yardstick says bling, bling, bling. Okay, all I'm doing is measuring out with this yardstick one ADMAP. Okay, I'm coming out one average distance to the mean. I'm just marking it down. It's a reticule. It's a grid. I'm laying down a grid using that. Okay, so that's what this thing means. And you're going to see this very often. And you have seen it before, and now we're trying to put it into context in business. Okay, so we could go out three standard deviations to the right. I'm sorry, 3 ADMAPs to the right, or we can go out 3 ADMAPs to the left. This is just a golden bar. We just made exactly 4.2 degrees Fahrenheit. Okay, so this is degrees Fahrenheit, and we're just marking it on the grid. It's a property here, and I'm marking it here, here, and here. Okay, so I have six equally spaced points along here. Okay, actually 7. Count the middle. All right, that's all we're doing when we're measuring that. We have to be able to describe how wide our data is using ADMAP. Okay, so remember what we had to do here? Okay, we had to take the absolute value of the distance because we weren't interested in what they call the vector. We didn't care what direction it was going in. We just want the scalar. We just wanted to know the magnitude of what that distance was. Oh, okay, we get that now. All right, that's fine. All right. Here's one little problem, okay? This is where most people come off the rails on statistics, okay? Don't worry about it, all right? I think if you all you have to do is remember this, and we'll be fine. And this really comes down to mathematicians exploit the sort of tools they create within the compromise that they also create with it, okay? So it's an interesting property in math that sometimes we need to explain things with some complex understanding. And at the end, when we finally get our solution, ta-da, we get an outcome here. Let's call it an S for solution here. A lot of the complexity goes away. They add complexity in here to be able to use, let's call it the calculus. All right, we're learning the calculus of of statistics here. Okay, what are the things we need to know? All right, and so what they find is that the absolute value of this distance, as they try to exploit it, goes nowhere. X marks the spot. It really doesn't work out for them. Okay, it's not something in math that works super great, is using the absolute value of that. So we have to find another way of coming up with a positive value there. And so with a little thinking, you're going to come up with, well, why don't we just square the distance? Why don't we just take that and square it? Hey, yeah, that's a great idea. And we'll divide it by n. Okay, all right. That's from I is equal to 1 to n here. Okay, why don't we just square that? That's a good idea. Well, the squaring formula gives us a positive number, but it emphasizes points that are further away from the mean. Okay, so that it's going to increase in size. This number, if we go with this equation here, right, there's something else that happens. We squared something in here. So that means this is in degrees Fahrenheit. What in the world does a degree Fahrenheit square mean? All right, so at some point we're going to have to take a square root of it. Okay? That's why the standard deviation is confusing to people, because if you don't understand what the initial interest was in it, was the simpler form down here, that's all we're doing here. And they had to give it a different name. And it's kind of like the standard deviation is kind of like an average distance. The deviation's a distance, this average distance. Okay, so the standard deviation has to do exactly with what I just explained here. All right, and notice that we take the square root of everything. Even though the numerator is the only thing that gets squared, we end up taking the square root of everything here. This is where most people wander off and say, I don't like math, or I don't get it. And that's all you have. This is the part that you have to remember what's going on underneath there. This is a tool. It's a construct. This is a arbitrary construct in math. And when we walk around with standard deviation, we know that there's this emphasis on points that were further from the mean that causes the standard deviation is going to be greater than that simple thing we calculated as the average distance to the mean of all the points. All right, it will always end up larger because it emphasizes distances, because you're squaring them. It gets larger the further you are from the x mean, from the mean, further you are that you are from the mean. Okay. So we got our add map. I'm just going to write it up here. This is our add map. It's useful, but nobody else uses it. That's the problem. Okay. So we're going to make this equal to, just bring it up. That's all. Just copy it over. We'll keep that in mind. Okay. So let's run out the rest of this. Now let's actually calculate the standard deviation. Okay. So what do we need here? We need this distance, which we already calculated. All right. We need to square that. Okay. So we're going to do the square of the distance. All right, and I'll even use the negative numbers because that's what this is supposed to fix. All right, so we're going to square raise that with a caret. That's Shift 6 on your keyboard. We'll square it. Excuse me. All right, so we're going to bring this down, and we're going to go on the home screen here, and we're going to drop a lot of those decimal places. Let's get rid of those. Just to remember that there's some precision there, we're going to leave them in there. Okay, so let's grab this. Oh, that makes it pretty tight. Okay, center them up so it's more readable. Boom, there we go. Okay, and you know what? Let's make a header column over here. Pretty that up a little bit. Throw on some blue. Let's plain in some white and bold it up. There you go. Hey, you know what? I'm even going to bump up the font on it. Okay, it's just makes it a little bit more legible. How about that? Okay, so let's center everything up in here. Okay, there we go. All right, so it's nice. Okay, there we go. Be kind to yourself, like in Excel. Use Excel to your advantage here. Okay, so we have the square. We have all the squares. We squared them all. We have to add them all up. Okay, so we're going to do sum of the squares, right? And that's just going to be equal to Alt. Equals is a shortcut for that. It's not going to guess correctly. We have to grab the column by hand, put it in there. So the sum of the squares of all these squares is 507. Okay. All right. So now we're going to take the average of that. All right. We're taking the average of the squares created. Okay. So let me put that up a little bit. The average of the squares is going to be equal to that number divided by 20. Okay, again, it's always with the great precision here. Okay, it's like overemphasizing precision. Okay, so average, so the sum of the squared and then the average of the squared, we're almost there. We just need to take the square root. Okay, so it's going to be this is going to be tricky to name. Square root of the average square size. Okay, is just equal to that. You can either raise it to 0.5 or you can run the, I think everybody else is going to want to run the square root function here. Square root, that's easier. Okay, well, let's get rid of that precision. You know what? I want to center these numbers up anyway. Center all this up. recenter some of this. Okay. Get rid of the precision there. What is this number we just calculated? This number that we just calculated is your standard deviation. That's how you calculate it, right? So, hey, why don't we run the standard deviation formula on our data, okay? So we'll run it on our data and see if we came up with the right number here, okay? So it's going to be equal to the standard deviation.p, that's population, of... Now, make sure you grab the right numbers here. We're going back to the original data, not any of these other pre-calculations or post-calculations we did. All right, and it came out to the same number. That always pays off in my videos when I don't have to stop and fix things, okay? Right? So I say that tongue-in-cheek, all right? I'm just going to throw a couple of digits on there so you know that the precision is there. It's just visually we're just representing it. It's data presentation. We're just presenting the number rounded to 2 decimal places, but it didn't get rid of the precision. If you do a round on a number, then it will cut off all those digits and you lose the precision and your calculations go wrong. They'll be off a little bit, okay? So there, we figured out what the standard deviation was, okay? So I'll put in here Control C, and I'll copy this over here. Still the standard deviation, but this is going to be by formula. All right, that's the story of numbers. That was a long path there. Now we're going to learn how to exploit this more. Okay, so to answer the questions, we're almost to the end point of answering question 10.1, which is a super common question in there. Okay, but before we touch that, we have to understand that what we're going to exploit out of this normal curve here is the symmetry involved with it. Now, if we go back, let's add another property to this. Okay, so the other property is that the area underneath this curve, especially when we have a sample, we have a finite number of sample readings here. We have a sample will have readings within it. Okay, so the readings there, we have a finite number of 20. And so when we look at a curve, down over here on the right, when we look at a curve, all the outcomes are contained underneath the curve. There's nothing else that will ever happen. This is the only thing that happened in our sample test here was we got 20 values. So the probability of any of these outcomes is 100% or 1.0. Okay, so especially when we have a sample like this, that underneath the curve represents anything that can happen. Okay, we kind of define that way. All right, so the probability under the curve is equal to 1.0, and if you multiply that by 100, you get 100%. Okay, so you can state it either way. But generally, we're going to stick to probabilities with a decimal like this. Okay, like 0.37 would be 37% probability. So that's the other thing. Now, we have some formula here, okay? So there's a fancy formula we don't have to know about, derive, or anything else. There's a fancy formula of formula along x, okay, as you move from left to right here when you have normal distribution, especially perfect ideal data here, is equal to something. And we don't have to worry about that. It's embedded in Excel, okay? We don't get into this. We use this as a tool. How many other things in our lives do we use as tools, like our cars? How many people really know how everything in a car works, right? Well, that's how we're going to get. We're going to treat these formula. There's several formula in Excel that operate on this. Okay, that we can give it different kinds of data, and it will give us the area, the partial area, up to a point. Okay. So the most frequent way that we deal with this is we look at the cumulative property, okay? I'm going to use a different color now. Now it gets interesting. I need some other colors here, all right? A really different color, like blue, okay. So we want to know what the probability of all outcomes up to and including some point on this X. That is the property that we're going to exploit the most here, okay? So if I asked you, what is the probability of getting a day where the temperature does not exceed 53.4 degrees? What is the probability of getting a day that does not exceed 53.4 4 degrees. There's different ways of stating this. You have to really pay attention to your words or state the question correctly that you want the answer to. Okay, so we want to have the area under the curve up to this. What is the probability up to including the average? Okay. Let me get rid of that coloration in there. Okay. Well, we just said that this is a symmetric, in ideal case, it's a symmetric curve. 100% of the curve, 50% of the curve is contained from negative infinity up to the mean. Okay, so this is 50%, and this is 50%. And we're going to use symmetry hugely. That's what we're going to exploit all the time, all right? So the kind people of Excel have come up with formula here, okay, that we're going to figure out what the probability is up to this point, okay? So we really built up to, I just want to re-emphasize something here. We really built up to, this was huge, to this. This is the formula for standard deviation, okay? We really built up to that. It was a long lead in, and I didn't want to go over there too fast. So this is your standard deviation is equal to that, okay? All right. And we're going to put things in terms of that bar. Remember, I should paint that yellow too. This is a big thing. This is the standard deviation over here, okay? All right. And before I go on, I want to explain. Remember, I said the standard deviation was going to be larger because there's distortion of the distance because we're squaring the distance. And that's going to tend to make your standard deviation larger than that original thing we were ever after. Okay, I'll include that in important things, okay? So the average distance to the map of all the points, okay, is going to be larger. The standard deviation is larger. So there you have 5.04 is greater than 4.2. Okay. This is the quality we ever started out after. Just keep remembering that it makes sense that the average distance to the mean of all the points is something that would describe how far away that bar, when we overlay it on the grid, this is a golden measure that we have, this ADMAP. But unfortunately, we're playing along with the rules of math and statistics. Anybody dealing with statistics has to buy into this and talk about standard deviation, not the ADMAP. Okay, so I will ask a question that says, what is the standard deviation like? Okay, and it's like if you remember the acronym, that's why I've made it into an acronym here. Okay, if you remember the acronym, I just had a problem with my pen. That's why there's marks all over the screen. Okay, so what is it like? What is the standard deviation like? It's like the average distance to the mean of all the points. That's how you remember this equation down there, all right? And that's a key. Hopefully that's like the Rosetta Stone. And you can go further, because the more things that you see where you work that are behaving along to normal distribution, you could actually use these techniques and look like the smartest person. No, you could be the smartest person in the room. That's the point of me going into this detail. Okay. I think most people turn away from it because this very core, this lesson here, I think is the most important lesson in operations class, both undergrad and grad. That's why I spend a lot of time on this, because it's a tool that many people shy away from, and you shouldn't. The big thing is push on the understanding, push on the numbers and the definitions in little problems that you come up with for yourself. Say, what happens if this? What happens if that? And you're going to start thinking like a mathematician. You're going to understand what the process is for a theoretical mathematician, how they come up with such things as these equations. You'll start seeing the process itself. All right. Okay, so we're still after problem 10.1. Okay, so how do we use it? How do we get there? All right, how do we exploit this? So we have formulas. Okay, so the first formula, let's start down here, is equal to the norm.dist formula that we find here is going to give us the area of the normal distribution curve up to a point of interest. Okay, so I've left little x here. We've left little x here, okay? And what it's going to give us is the z value, okay? So we now have to introduce what is a z, okay? This may be the last little bit of a hurdle to get through, okay? So I'm gonna get away from starting my norm.dist to explain what the z value is, okay? So what we do is the z what a z-table is, you've seen them before. I think everybody's seen this before, and now I'm just trying to wake up the brain cells that were trained earlier that you haven't used for on this right now. But this is in our this is in the natural units of the problem. It's in degrees Fahrenheit. Okay. Now I did say we were going to exploit this. Everybody, scientists of all kinds, whether it be biology, nuclear physicists, virus people, behavioral psychology, everybody uses this. So there's this common tool called the Z. Okay. Let's simplify this calculation of this area, everybody. They all said, yeah. Okay. So the big math conference, everybody says, yeah, let's figure this thing out. Okay. So what we're going to do is figure out a Z. And what that does, I'm going to draw a new picture here because I need some left-rightage here. I need some space. Okay. So what that does is it says, here's where our native units are. Okay. That's supposed to be, whenever I draw this, my pen, this pen pad sometimes slips a little bit, it gets crooked. This is supposed to be drawn as a perfect ideal normal distribution like this. Okay. And here's our natural data, 53.4, and we know that our standard deviation that we're now using is 5.04. Okay. So that means we're going to mark down one standard deviation down here is down minus 5.04 from 53 point whatever it was. Okay. So this is going to be 53 minus 5 is approximately 47 degrees, correlates to this point here. And we're going to keep subtracting another one, another 5.04, and another 5.4. Okay. All right. So that's our native data. Our natural units of data is in Fahrenheit. And the tool that we get to, okay, you're going to see this, is just a z-curve. It's the same thing. A z-distribution is the same thing as our distribution. Okay, so we have whatever distribution we have here. It's marked by a mean and it's marked by a standard deviation. All the z is a common place that biology comes to, that psychology comes to, however you say psychology, which business comes to, which we had science there, maybe economics. All these different fields come using the z. That's why it's there. Okay. So you can talk to people from other fields, and we're using the same basic tool here. And if you look at what the equation here is, what we're going to do is we're going to shift this thing down. Everybody's going to normalize their own native data, and instead of the center point being the mean, it's going to be 0. We want a 0 base. This is going to be the normalized. Everybody's coming to the normalized model now. Whole world comes down to this, so we can all go to this very same table on the internet or the back of your books, okay, and I'll show that in a second here, so that we can all use the same table. And what we do is we come down to this, and then we come back to this, okay, so that's what we're doing. We're coming down to a common calculation area here, okay. So the z, what we do is we take whatever point of interest we have, and we see how far away it is from the mean. Okay, so remember our little blue X here? I'll put it up here. Okay, so we're always going to be interested in our little blue X. It's right about here. Okay, all right. So that's going to be a point of interest. Go back to my happy green here. Is it that color? Yeah, that's the color. And what we do is we're going to shift. If you took every point in our data set and you subtracted the mean, you would move it down. It would be subtracting it. You're taking the numbers off, okay? Until, well, look at it. What if you put the mean into that and subtracted the mean, right? You're going to get 0. That's why it's center-based. So for all points left of our mean, they're going to end up down here in negative territory, and all the positive points will end up here in the positive territory. We're just 0 basing it, okay? And then we shifted it. This is called translation. So we translated it or shifted it. We translated all our data down and 0 centered it. Okay, so we 0 centered it where it was centered around our mean. Okay, and then we're going to scale it. We're going to scale it to that bar. This attribute of our data was for us the average distance to the mean, and our data was this is our standard deviation. Right? So all we do is scale it. So it comes down and then it gets scaled. All right. I should use a different color on that. Some hideous. I don't even know what this is. Okay. So what it then, see, right now we haven't scaled it yet. So it's still 45 degrees to 65 degrees. But what we do is it's all, what is a z? A z means how many standard deviations, okay? So when you get down here, it's going to go 1, 2, 3. This is one standard deviation, 2, and 3. This is exact, well, actually minus, okay? So we're in -1, -2, 3 territory down here, and we're in 1, 2, 3. See, what we did was we shifted it and then we scaled it. So we're just talking into really a z is how many standard deviations the point of interest is from the mean. Okay, so our little blue x we're trying to protect here, we're still interested. So the x translates from 47 degrees to something shy of -1. Okay, we just shifted and scaled it, so it's going to be like point. I don't know what it's going to. We don't know yet, but it's going to be less than -1. It's going to be -0.9. Technically, it's greater than -0.1, but it doesn't exceed into the negative range beyond -0.1. It's within its relative distance is still where we had it up at the top of the hour as it is now. This video is going a bit long here. Okay, so that's we're just about there. So z you have to understand is I use the correlation to anything like a horse race or NASCAR is really good, but you listen to a horse race and everybody has kind of an idea. Oh boy, I don't know, how do you draw a horse? What does a horse look like, right? So everybody has an idea. It's a horse with a thing on it. All right, how long a horse is, just kind of visually. I don't even know how many feet it is. 11? I have no idea, right? But when they're racing, at the end of the race, they said, won by a length. And so in horses, we kind of come down to an unspecified but accepted kind of a length of a horse. In NASCAR, he won by half a car, So a car becomes the standard. You understand? That's what your standard deviation is in here, okay? We kind of use it to compare other things. So we're comparing the distance to the standard deviation now, okay? So this becomes a dimensionless because standard deviation is in degrees f and our distance is in f. It's dimensionless, but if you think about it, it's how many standard deviations we are to the left or right in the world of z. So this is another power equation that we use, or concept, right? So those are the major parts that we have to remember. These are the ways we exploit the fact that so many things we study end up being normally distributed. Okay, so we're almost there. Okay, this you have to get down to really move forward. And the more that you spend time with this and get comfortable with it and push it around, you get comfortable about this by asking yourself questions and then trying it out. Okay, it's very difficult to read this linearly. It doesn't make sense until you draw pictures and push it around and understand what's going on underneath it. Okay, so let's take a look. I'm going to go capture problem 10.1. Okay, so I've dropped in the problem here. I've reproduced it. And if you read through this, specifications for a part for a DVD player state that the part should weigh between 24 and 25 ounces. The process that produces the parts has a mean of 24.5 and a standard deviation of 0.2 ounce. How do we use this information here? The distribution output is normal. Okay, we assume it's normal because why would we waste our time if it was anything but normal? Okay, so they're talking about using table A here, but we're going to use a formula. I think table A is probably the Z table. Pretty sure that's what it is in the book. Okay, so we're going to use the Excel to do this. So here's the important part. Our process. Okay, so our process, again, one more time, I'm going to draw the normal distribution here. Make sure I have a good colored pen. What am I working with? I like red. It seems to show up on the screen better for people. All right, so let's draw what's going on here. So we have a process. Okay, it's normally distributed. All right, it says it has a mean of what? It had a mean of 24.5, 24.5, and a standard deviation of 0.2 ounce. Okay. Here, so hang on, people. Here you go. Here's something to understand. If you look at a drawing of the normal distribution like this, and it's ideal, okay? So we're saying we have ideal data. It's a perfectly drawn normal distribution here, okay? And we measure down from the mean 1 standard deviation, 2 standard deviation, 3 standard deviation, all right? if you're dealing with the ideal image of it like this, right? Go up 1, 2, and 3, okay? I could put this in front of you. I could put without the tick marks in here, I could give you this and I can say, okay, on perfect ideal normal distribution, where, if we measure out from the center using a normal distribution ruler, okay, if we go out 1, 2, and 3, where do they occur on the curve? The first one is, see, I'm just coming up from here. I measured over here and I'm looking at where it intercepts. Okay, so we're going to draw the intercepts of the curve up from where I've driven the tick marks. I've just measured out, they said 0.2 ounce. Okay, so we're going to come down 0.2, down another 0.2, down another 0.2. Okay, then we're going to go up 0.2, and we're going to go up 0.2, we're going to go up 0.2, and these tick marks have values, right? 24.5 goes to 24.7, 20. I did the wrong thing. Control Z with the wrong direction. Not 7. It should be 22.3. I'm coming down. I'm subtracting 0.2, so it should be 20. What did I say? 24.3, and then 24.1, and finally 23.9. Got it? So these are distances. The 0.2 is your standard deviations. We just use that to set up a grid. And when you do that, your plus and minus 1 standard deviations will always end up on the shoulder. And then if you go out plus and minus 2 standard deviations, they will always end up in the middle of the curve, just about. And the third is going to end up down toward the skinny part of the tail. This is like a classic look. All right. So this you could get a tattoo of on your eyelids, inside of your eyelids there, and be happy with it, because this doesn't change. This is now all that previous information that I just went through. We're locking into how do we actually use this thing. These are going to be reference points, okay? If you just remember what's going on with this drawing, this part of the drawing, you can look at another problem, all right? And you can find a point of interest on here, and you could come up with close estimates as to what the probability will be for the point that you're interested in. So we'll put 24 is going to be right between 23.9 and 24.1 on this curve. Somewhere in here, okay? And if we go up to 25, all right, let's mark off what our gradations are up here. So 0.2 up, we're going to be 24.7, 24.9, and 25.1, okay? So on the upper spec limit, okay, got that? So the upper spec limit is right between the second and third standard deviation, right between them, okay? So this is what the customer sets up, okay? Now, our process can vary. On one day, we might have a really great day where we're making more things near the mean, and our curve would look like this. We have many more things near the mean, okay? So with the sort of, if we want to call it this, the goalposts, okay, so the goalposts are what the customer sets in stone, and our process is moving all over the place. Some days it might shift down. We might be way shifted down like this. Other days shifted up, or it could be really bad day where we're not making anything near the mean. Like a lot of things are falling way far from the mean. Okay, and that's why I like to be able to do this recording, to be able to show it dynamically. Let me draw those in here. Okay, to draw this a little bit more dynamically, it's better to explain things that what you're looking at. It's so static to just look at one curve here. But let's say today, this is what our production is. It says we're going to reject, the customer's going to reject everything below 24 and above 25. We're reject. So this is reject. Okay, and these areas are equal. Okay, so the idea is we're really exploiting the symmetric properties of this curve, the normal distribution here. Okay, so what does it say? What percentage of parts will not meet the specs? Okay, so we need A plus another A. That area is going to be the same. Okay, so how do we do that? We use the Z. Okay, so this is the way it's all set up. So these are tools that have been set up for us. Okay, we had talked about the Z. And most times, if you've had statistics before this, the Z score, which we calculate, the Z score leads to the Z table. And somebody this is actually what they do, and usually in class I would do this, but we don't have enough time this semester, is we take a sheet and we actually create a z-table, okay? And what a z-table looks like is usually you only need half of it because of symmetry, and you just add parts that you need by looking at this. You have to understand it visually here. That's why it's so important. And what we do is we come into the z-table, all right, and what do we do? There's a range of rows here, and it will usually go from like -3 to 0, okay? So that represents from here down to, I'm sorry, the other way around. Let me draw it the right way. It would be from -3 to 0. See that span up here? Okay? From 0 to 3. If you need other numbers, you need Excel. If you need to go more negative, if you need to know the area up to a point that's even more negative to this, then you have to use Excel or find a better table. But you can find these tables all over the internet, right? So when you come in here, usually it starts at -3, -2, -1. So it's going to be -1. And the way that this looks is on your table, okay, the rough number to the tenths digit is on the left, and then you add 0, then there's 0.1, 0.2, 0.3, all the way to 0.9. So you get, I'm sorry, 0.01, 0.02, 0.03, all the way out to 0.09. So these are the hundredths digits across the top, and tenths, it goes to the tenths here. And what you do is you say, if I need to know what 2.01 what the z-score for that is, okay, I go to this part of the table. See, there's the 0.01, and I add that to 2.0. So it'd be 2.01. And what do we find here? Okay, a lot of words around this thing. This is the thing with the statistics. There's a lot of words about what's going on. But this finally gives us the percentage. What comes out of here is this table's filled with numbers that will range from almost 0, the further you go away from the mean. Okay, so the middle, rather. This is like the middle of it. This is z is equal to 0. Okay, so if we're way down in this negative range, there's z equals 0. If we're way down in the negative range on z, we're going to get tiny little areas after a certain point. They're almost negligible depending on what you're working on. Okay, so what we would do is we'd go in here and we'd pull a number out, okay? And the way that these tables are generated is they would use something like Excel, and they would generate the table and then print it out and put it on the internet. There's an Excel function here that we can use to get the area to the left of any point along this line, and we'll punch that in right here, is equal to norm.dist formula is kind of your plain vanilla. When you're entering into one of these problems, it'll give you this area, as we just said. So we need to know what point to go up to, and they said 24 is a lower spec limit from our customer. The mean is 24.5. Right? And the standard deviation is 0.2. And we punch true in here because there's two ways that this formula works. If we used false, it will give us the height of the curve at the point. And if we type in true, then it gives us the area up to and including that point. Hit enter. Okay. So the area next to that point to the left is such, and we need 2 times that because we have the same area because of symmetry above it. Okay, so it's an equal to 2 times that. So the full area of rejection is, this is going to be 2a is equal to that. Okay, so let's turn that into percentage, and that would be 1.24%. Okay, so our scrap is 1.24%, and we're interested in yield. Okay, so what's the yield? It's going to be 100% minus that. Yield is equals 100 minus 1.24, but we'll use precision here. We'll actually use the precision that Excel gives us, and that's going to be equal to it's going to be 1.0, which is 1, minus, and so we have a 98.75 yield. Usually you're interested in yield. What do they ask us here? What percentage of parts will not meet specs? There's 1.24. That's our 1.24 there. Okay, so now we're going to ask, this is a typical typical company question. Okay, well, wait a minute. Within what values will 95.44% of sample means of this process fall if samples of n is equal to 16 are taken? So we're talking about a reduction of confidence here because we have a smaller sample set. But we do know the mean of the population. We were given the mean of our population is 24.5. Okay, so that's going to be the difference between using a Z versus a T distribution. Okay, because we do know that we usually go with Z. The rule is also that if the number of samples is less than 30, we normally go with T, but we're overriding it in this case by saying that we do know the sample mean. I'm sorry, with the population mean up there. So the reason this is different is we're picking an arbitrary point. Okay, let's go with this. Okay, so we have always draw your normal distribution. Here's your distribution like such. We have some kind of mean going on here is 24.5. That's our the process ability or process mean is 24.5, and they're asking. I have some kind of reversing colors here. They're asking, okay, what points? Now we're going to back out if our yield is equal to 95.44. Okay, so what is the area? Now we're going to have to probably look at what the area is that is complementing the yield. We're looking at the scrap. What's actually that? Okay, so what we need to do is find out one minus point. What was it? 9544. Okay, and we're going to take half of that, right? Because we're going this direction. We want to know just to the left. We just want to know half of it. Okay, we want to know the actual percentage there. Divide that by 2. That looks good. Just double check, make sure it looks right. So 2.28% of our curve comes up to there. Now what is that? We need like the inverse of the norm distribution that we just ran. Okay, so the formula that we're going to use to get the z value, we're going to take equals. Try that again. Is equal to norm dot s dot inverse of a probability. Okay, so we're going to click in there. That's our probability. So we're learning the second formula that's commonly used here is going this direction. Okay, we set some arbitrary limits. We're moving through the problem kind of the other direction that we moved from before. Okay, so norm.s.inverse of that probability is equal to -1. Boy, that's really close to 2 if you ask me. Okay, so I think we're going to end up using 2 for that. Okay, so we've got the z here, which is close to 2. Or -2, okay? And for the purpose of x bar, what we do is we're just going to use the positive value of this because I'm going to drop this in here. Okay, so this is the explanation of what an x bar chart or an x bar approach means to us here. And the thing is that we're degrading the variability here through, if you take a close look at what's going on here, x bar, okay, is the average of the averages. That's really what we came up with when it says up in the upper part of the problem here, and it said that our mean was such and such. Well, we didn't do the whole population. We took a bunch of samples. So there's sample 1, sample 2, sample 3, all the way down. And with every sample, we took a number of readings. It could have been 5 readings. It could have been 100. It could have been 1,000. And so of these readings, okay, we would take the average reading here, okay, and it's going to be weight. So it's the average weight of these samples. And then that's what led to the 24.5 is the average of these averages. So that's what's implied in this problem. And that's why actually I've made this part of the video here is to cover out what's going on between the lines here. So you had to choose which mechanism you're going to use to analyze this with. Okay, so that's what your x bar, it's an average of averages, is x double bar here. And we figured out what z was, but we have to degrade it. All right, so the units are being held constant. Remember, we have ounces, okay, OZ, I guess, OZ, and your standard deviation is going to be in OZ, okay? And so that's the standard deviation of the sample. So it has a little X bar there. So that's the standard deviation, the variability of when we did all those samples. How much did the averages change by, okay? That actually gets degraded from the standard deviation that we know about. Okay, when we do a sample, it has to get degraded, and the sampling here is 16. The number up above in the problem was 16, right? We'll go back up here. It said we took n is equal to 16 there. Right, so let's back this back out. So what we're looking at is that, let's take a look here. So this is x double bar, normal distribution, like such. That's our mean. We know this range of some percentage, and we're backing out the answer. Okay, so we're given one part of it, and we're getting another. We're reversing out what it was. We had a 90, what, 2.28 is it? Came out to be. So what I had up there, like 2.28, it's down below here, 2.28. We have to find the numbers associated with this, and again, because it's a sample here of 16, we have to degrade the standard deviation that we were given. We have to degrade that by the number of, dividing by the square root of the number of points that are in our sample set here. Okay, so x bar, double bar is going to be equal 24.5, right? And so we need plus and minus. The number that we came up here with, we're going to just take the absolute value. We just need the magnitude of the z. We don't need the direction. Okay, so we're going to add the z, but degraded by 0.2 divided by the square root of 16, which would be 4. Okay, and that's going to be the upper control limit. Our lower control limit is going to be 24.5 minus the 2, 0.2 by 16. Okay, so let's figure out what those numbers are. I'm actually going to use the real number we came up with. I just wanted to use that. Remember, I said it's almost minus 2. Okay, so I'm going to actually use the real numbers here. Okay, so that's just equal to 24.5. Here we're going to do plus our z times 0.2 over the square root of 16. Okay, so we have to finish off all our parentheses here. And we get 24.59999, so it's probably 24.6. And then what I'm going to do is I'm just going to text copy this. I double clicked in there, Control C, hit escape, and I'm going to drop this down. It's the same equation, only we need to subtract. Put this minus sign, and we subtract. Okay, so those are the control limits associated with a 95, here's the number here, 95.4445% yield. Okay, there you go. Oh, just double check on the answers there. We'll come back up here. And we have the lower value is 24.4, the upper value is 24.6. So if you round it as they had asked, okay, so the problem, it asked you for 2 digits, you would get the right number. If you just round that, you'd get 24.6 and 24.40, okay? You get the right answer. So that was a long path to solve this problem, but this is the lecture that I wish we had last Monday when we got kind of interrupted now that things are kind of interesting. People are on Macs and PCs. So hopefully this was helpful, and we'll see you again next week in class. Let me know if you have any questions in the meantime.